All right, so now we've learned a little more about derivatives and what they are, and we've seen how we can define the derivative as the limit of a difference quotient. What we'd like to do is start developing sort of shortcuts, essentially, differentiation rules that will help us find derivatives of functions without necessarily having to go through that entire limit process every time. So what we're going to do is we're going to look at some generic situations with some sort of arbitrary, unspecified functions, and then we're going to try to use the limit idea to come up with a rule that we can then apply to help us do derivatives much more quickly and easily. So the first one, first of all, we're supposing that we have two functions f and g which are differentiable. And we're going to have c represent some arbitrary constant. So in earlier videos, we were using c to represent the number at which we are calculating the rate of change. But here, c is just going to be a constant that we can either add or that we can multiply by or whatever, just a constant. So the first example I'm going to look at is a constant multiple of a function. All right, so let's figure out what is the derivative of a constant multiple of some differentiable function. Okay, well, we're going to come up with a rule that this equals something. And what we're going to do to figure out what that rule is we're going to look at the limit as delta x approaches 0 of this guy, constant multiple of the function f, first evaluated at x plus delta x, and then constant multiple of function f evaluated at x, and then all over delta x. So that would be the derivative. Okay, by definition, this derivative of the constant multiple of f is this. And then pretty clearly we can see that this constant multiple can be factored out, right? So let's do that next. C multiplied by f of x plus delta x minus f of x over delta x. So factoring that constant out, now we can see this is just the limit of the constant multiple of something, right? This jazz over here. And we had this rule that we learned about for limits, which was that the limit of a constant multiple of something is a constant multiple of the limit of that thing, if that limit exists. And since we're assuming that this f is a function which is differentiable, that means we're assuming that this limit does exist. So we can just take that limit, whatever it is, and multiply it by c. And that would mean, since this limit is by definition the derivative of f, that would mean that we have the constant multiple of the derivative of f, right? So this would be c times f prime of x. So essentially what we're saying here is that if you take the derivative of a constant multiple of something, it's that constant multiple times the derivative of the something, right? Essentially the constant multiple just stays around. It doesn't... nothing happens to it, it just sticks around. So constant, this is called the constant multiple rule, for obvious reasons. All right. Okay, second one. Let's do, we might not have quite enough room on this paper. Actually, I'm going to flip it over and do a new paper. So there's the first one. For the next one, let's do the derivative of f of x plus g of x. What's that going to equal? I bet you can guess, but let's explore it and find out. So we're going to do the limit. Delta x goes to 0. And then we have to take our f of x plus g of x and apply and put in x plus delta x to that function, which means everywhere we see the x, we're going to replace it with x plus delta x. Then we have to subtract the original function, which we're going to subtract the entire thing, so I'm going to put it in parentheses, f of x plus g of x. I take that whole thing divided by delta x. All right, what can we do with that? Well, we can distribute this negative up here. So we've got each of these is going to be negative. And then actually, I'm going to kind of skip a step, and I'm going to combine two steps, perhaps, and rearrange things as well. So I'm going to be subtracting each of these, and then let's rearrange it into, we've got this term, f of x plus delta x minus the f of x, and then plus the g of x plus delta x, this term, minus the g of x, like that. And this whole thing is still divided by delta x, but I can distribute that division in this very strategic, specific way, like that, so that this here is the difference quotient for f, and this is the difference quotient for g. Then we learned all these properties of limits, and one of the properties of limits was that the limit of a sum is the sum of the limit, right? So we can essentially split up the limit and do this limit of each part separately, and then add those results together. If they exist, which they do, because we're assuming these two functions are differentiable, and these two expressions we're looking at here are literally the derivatives. Okay, sorry, I have to switch to pen or something because that pencil is not working. Gonna have to grab a new pencil for the next video. So as you can see, this is just the derivative of f plus the derivative of g. So what we see here is differentiation of a sum of functions essentially distributes over that sum and gives us the sum of the derivatives of those functions, like this. And if instead of addition, if this were subtraction, this would all work out very similarly, where that's a minus and that's a minus, and then this becomes a minus, and this becomes a minus, and this becomes a minus. And then if this were in fact subtraction, this would be subtraction as well. So this is called the sum, these are called the sum and difference rules for differentiations, for differentiation. Bleh. Okay, next one. So for this one, let's look at the derivative of a constant function. So just the derivative of c, where c is constant. What is that? Well, by definition, limit as delta x approaches 0. Essentially, like think of this constant function as our f of x, right? Remember, we have to do this. I'll just write it out as a reminder. Difference quotient there. Except f of x plus delta x is equal to c, because f of x is always equal to c. It's constant. And f of x is c. So this is just, and this is kind of like comically simple. It's just c minus c over delta x, right? Each of those is outputting the same constant value. So that's 0, and so this is 0. 0 over delta x, right? If our numerator is constant and equal to 0, then yes, this is going to be 0. So the derivative of a constant function is 0. And this makes so much sense when you think about it graphically, because a constant function, if this is your x and y axis, your constant function is a horizontal line at height c. And what's the slope of a horizontal line? At every point, at every x value, the slope of that horizontal line is 0. So the derivative of a horizontal slope, of a horizontal line, should always be 0, right? So hence why we have this rule. Okay. We can do better. Let's keep going. What's the derivative of x? That's the next, this is the constant. If the constant function is the simplest function you can think of, the next simplest has got to be just like the identity function, y equals x. So the question would be, what is that one? All right. We know the drill, right? This is going to be x plus delta x. That's my f of x plus delta x. It's just itself. Minus x, right? Because it's minus f of x. It's just x over delta x. Our x's cancel out, and we get the limit of delta x over delta x, which is the limit of 1. My delta x is approaching 0. That got a little off there. But the limit of 1 is just 1, right? So that's just 1. And this also makes sense when you think about it graphically. You put your x and your y-axis down here. And what's the graph of y equals x look like? It is this line, which is a line with a constant slope of 1. So that derivative is 1. Let's do one more for this video. Let's do the derivative of x squared. Okay, what's that going to be? Well, we'll look at the limit. For this, we're going to have to do x plus delta x squared minus x squared over delta x. So there's our a limit of difference quotient for that function. And then to evaluate this, I think we've actually done this exact problem before. This feels really familiar. But to evaluate this, we need to expand that squaring, right, like that, and then we've got the minus x squared still. Right? And after expanding the squaring, then we see the positive x squared and the negative x squared cancel out. And we can then, for the remaining terms in the numerator, they all have at least one delta x factor, so we can factor that out, which leaves us, if we remove one delta x factor from each term after factoring out, we have that, 2x plus delta x, still divided by delta x. Now these are common factors which cancel, and we're left with just the limit of 2x plus delta x, which as delta x approaches 0 is going to be 2x. So this function's derivative is 2x. That's where I'm going to cut off this video because it's getting a little long. We're going to go further, okay? So just hang tight.